Hello everybody and welcome back to Algebra 2. Today we're going to be talking about 5.2, polynomials, linear factors, and zeros. Let's begin. So let's start off with a little vocabulary and review. Cross out the expression that does not have x to the fourth as a factor. Essentially, all this is really saying is there can't be 4 x's. If there are 4 x's, then x to the fourth will be a factor. So if we have x to the fifth power, that is like us saying that we have 5 different x's. Because x to the fifth power is x times x times x times x times x. Which means that we have 5 of them, which means that we can take out 4 of them and we're still left with something. Whether that's 1 or in this case an x, that doesn't really matter. But we are left with a certain number where x is not in the denominator. Therefore, x to the fifth does have an x to the fourth as a factor. 2x to the third, however, does not, because there are only 3 x's, so we can actually cross out 2x to the third power. X to the third times xy is really x to the fourth times y, because there are technically 4 different x values. We have 3 in the beginning portion, and then we have the fourth one that is attached to that y, so that is a-okay. That does have x to the fourth as a factor. And whenever you have a variable with an exponent that is being raised to another exponent, all you have to worry about doing is essentially multiplying these two numbers together, giving you whatever they end up being. So if I were to actually go through and simplify 3x squared, that will be 3 squared, which is 9, and the x squared would end up being x to the fourth power. Sure enough, there are 4 x's, which means x to the fourth is a factor of 9x to the fourth, obviously, as you can see. So we are actually not going to cross that one out. So the only one that we can cross out is that second portion. Circle the factor tree that shows the prime factorization of 14x squared. In order for something to show prime factorization, that means that our end result can only be prime numbers. Prime numbers being numbers that multiply between 1 and itself, and that's it. There are no other ways to multiply to that number. Like 14 is not a prime number because we can write it as a 2 times a 7. However, a 2 and a 7, both of those are prime numbers. There are no numbers other than 1 and itself that will give you a 2 or a 7. That being said, same thing goes for the x as well as the x by itself. Knowing that the very first factor tree shows prime factorization. 14 right here is not a prime number, and that's why we can't use the middle. And the 2x is actually just literally, it's not 1 times 2x to give you 2x. You can also have the 2 times the x to give you that 2x, and that's why 2x is not prime, and the same idea goes with that 7x as well, meaning that this is not fully factored down to the prime number, meaning that this tree does not show prime factorization. Vocabulary builder. So for today, the vocab word that we're really going to be focusing hard on will end up being the turning point portion. Now, turning points can also be referred to as relative maximum and relative min. Seeing how when we start talking about these, we're not going to be talking about the endpoints, and the endpoints are always going to keep on going on for forever. We always will have those points at which it changes direction that we can kind of relatively call a max or a min. Alright? A turning point is where the graph of the function changes from going up to going down, or from going down to going up. In other words, it kind of makes that little 180 turn, that little spin around. Alright? Write the letters of the points that describe each turning point in the y-intercept. Now, in order for something to be a relative maximum, that means that at some point in time it was a highest portion if it wasn't for the fact that we ended up ending with the arrow going on to infinity. Alright, so in this case, our relative maximum would happen to be at b, because at one point that was the highest point that you could possibly get before we went on to infinity. So our relative max is b. Using that same idea, if it wasn't for this beginning arrow going to negative infinity, or just to keep on going into the negatives, our relative minimum would happen at e, because that at some point was our lowest point before we started increasing. Our x-intercepts, whenever it crosses the x value, or the x-axis, that is what you'll get. So our x-intercepts are going to be a, c, and f. Our y-intercept is going to be where it crosses the y-axis, which is at point D. Now we have to place a check if the sentence shows the correct use of the word turning point, or place an X if it does not. The turning point in the story was when the hero chose the book instead of the sword. Well, I'm not too good at English, but I will say that that does sound like a turning point. It does sound like a climax of the story, whatever it may be. The function has a turning point at x equals 17. Well, however, you can't say a function has a turning point where it crosses the x-axis. That's not necessarily true. Now, it very well could have it when it hits the x-axis, but it will never cross the x-axis, causing a turning point. Alright, remember, a turning point is a singular point in which it changes direction. So if it were to cross the x-axis, that would mean that it would have to increase past the x-axis as a whole before it actually did the turning point. So crossing the x-axis wouldn't work. Problem 1. Writing a polynomial in factored form. What is the factored form of x to the third power minus x squared minus 12x? Well, in order for you to factor, the very first thing that I'm going to notice right off the get-go is the fact that, well, each and every one of these share the same common variable, and that's the variable x. So I'm going to factor an x from each of the terms, which is basically like me saying, hey, I'm going to divide by x from each and every one of these terms. So x cubed divided by x will give you that x squared, because if you were to do it backwards, x times the x squared will give you x cubed. X squared divided by x will give you that x on the inside, keeping the sign. 12x divided by x will give you 12, again keeping the sign. Complete the factor table, then circle the pair of factors that have to have a sum equal to -1. Essentially what we're going to be doing is they want to take this quadratic trinomial, the x squared minus x minus 12, and factor it down into two separate binomials. In order for you to do that, you have to figure out what will multiply to that -12, but eventually add to a -1. Or how I like to put it, what multiplies to 12, but will subtract to a -1. Looking at all the factors of -12, you will have stuff like 1 and -12. Well, if we were to add both of those together, it would be 1 plus a -12, which is -11. You'll have -1 and 12, which would end up giving you that positive 11. So again, not -1. 2 and a -6 will end up giving you a -4. We have a -2 with a 6, which will give you a positive 4. And then we finally have a 3 with a -4, which as you can see is already circled, which is going to give you that -1. And we do technically have the opposite version, but that's going to give you a positive 1. But the one that we're looking for needs to be a -1, and that's why they circled the 3 and the -4. Therefore, if I were to completely factor this out, I'm going to rewrite the x and the x squared minus x minus 12, and then if I were to simplify it even farther and factor it out even farther, we would get an x times the x plus 3, because the 3 is positive, and then you have an x minus 4 because the 4 is negative. And sure enough, that is how you would go about factoring this polynomial form. Problem 2. Finding the zeros of a polynomial function. What are the zeros of y equals x times x minus 3 times x plus 5? And can you graph the function? Well, we're going to use the zero product property to find the value of x in each of the factors. In this case, the zero product property basically states that if we were to take each and every one of these numbers, the x minus 3, and the x plus 5, because all of these are technically numbers, we just don't know what the x value is just quite yet. But if any of these were to equal 0, that would mean that since we're multiplying by 0, everything else would turn into 0. So essentially, if we wanted to figure out what would the end result of 0 be if we had x equals 0, well, it literally is going to be that, x equals 0. There's nothing that we have to change. It straight up tells you that x equals 0. However, doing that same idea, we have x minus 3. Well, x minus 3 will equal 0, so we have to solve for x. So we're going to add 3 to both sides, and that's how you get x equals a positive 3. Vice versa, we can also do the same exact thing with the x plus 5, only in this case, instead of adding the 3 over, we're going to be subtracting the 5 over. So you get minus 5 from both sides, and you get x is going to equal a -5. Therefore, the zeros of y equals x times x minus 3 times x plus 5 will be 0, 3, and -5. So if I were to graph these, I know that my 0 are going to be attached to the y values. So now I have the x value of 0 with the y value 0. We have the point 3, 0, and we have the final point, which is negative 5, 0. And if I were to go ahead and graph it, I'm going to be looking at the points somewhere around this region, and this region right here. And sure enough, that is exactly what our graph ends up being. Those are your x-intercepts. Great job. Now let's go over a little bit of a theorem. In this case, we're going to be talking about the factor theorem. The expression x minus a is a factor of a polynomial if and only if the a is a 0 of the related polynomial function. In other words, circle the zeros of the polynomial function that is given the x minus 2, x plus 3, and x plus 4. Basically, all this is saying is that in order for this to be a factor, we know that these have to equal 0 at some point. Or in other words, it needs to be this area in which it starts to cross the x-axis. Alright, so in order for me to go through and figure out the zeros for these, you have to kind of take it step by step. Well, if we have x minus 2 inside the parentheses, you can go ahead and solve it out by doing x minus 2 equals 0, and then you add the 2 to both sides, and you'll end up getting a positive 2. Or you can realize that we're just doing the opposite. So we have a positive 3 right here, so the answer is going to be a negative 3. And if we have a positive 4 inside the parentheses, once again, we are going to be getting a negative 4 as our previous answer. A polynomial equation q of x equals 0 has a solution of negative 2. Cross out the statement that is not true. Now, if the solution is negative 2, that means that the root is going to equal negative 2, and the x-intercept is going to be crossing at negative 2. So in this case, the x-intercept on the graph of the equation is going to be at negative 2. That's accurate. However, the factor of the polynomial, the thing that we multiply to get to the original equation, is actually not going to be negative 2. In order for that to happen, we would have to actually need it to be x plus 2. So the final portion is not correct. The factor of the polynomial is not going to be an x minus 2. It's supposed to be x plus 2. Problem number 3. Writing a polynomial function from its zeros. What is a quadratic polynomial function with zeros, 3, and negative 3? Well, the polynomial is found below. Use one of the reasons in the blue box to justify each step. In this case, we're going to be doing the zero product property. So essentially, they did it backwards. We know that the x is going to equal a positive 3 and x equals a negative 3. So in order for me to do the opposite, I'm actually going to be moving the 3 and that negative 3 towards the x, giving myself it to equal 0. So I'm going to subtract the 3, and I'll add the 3. And that's where you get the x minus 3 equals 0, which is essentially what that first factor is. And you'll get x plus 3 equals 0, which is what the other factor ends up being. You can also think about it as, in order for us to go from this point, the factored portion, to the 0 portion, you just really have to do the opposite signs. That works as well. Knowing this, though, we can then use the distributive property. In other words, just basically make sure we multiply everything out. The x times the x times the 3, giving the x squared minus 3x, and that plus 3x, and then the minus 9. And then we are going to combine like terms or simplify. When we go through that, we'll get x squared minus 9 as our full answer. Problem number 4. Finding the multiplicity of a 0. What are the zeros of f of x equals x cubed minus 4x squared plus 4x? What are their multiplicities? And how does the graph behave at these zeros? Well, essentially, multiplicity means that we need to have a certain situation where some of these answers will happen multiple times, meaning we might end with an x plus 2 squared. If we end with an x plus 2 squared, we'll run into a situation where our answer will only equal x equals, well, negative 2, because it will be x equals negative 2 and negative 2, and there's no reason to multiply it twice or put it in twice, so we call this x equals negative 2 with a multiplicity of 2, and you can kind of base it off of the degree at the top. So if I were to go through and factor this problem out, the very first step I'm going to do is pull out the x value. Alright, and that'll give you the x squared minus the 4x plus 4. And then I'm going to factor out that x squared minus 4x plus 4, giving you an x minus 2 and an x minus 2. The factor x will appear only one time at the very beginning, so the number 0, or when x equals 0, will only have one multiplicity. The factor, however, x minus 2 appears 2 times, so that the number 2 is the 0 of the multiplicity, in this case, twice. The graph looks close to a linear function at 0 and close to a quadratic function at 2. Problem number 5. Using a polynomial function to maximize volume. The design of a mini digital box camera maximizes the volume while keeping the sum of the dimensions at most 4 inches. In other words, it's not bigger than 4 inches if you were to add up all of the length, the height, as well as the width. If the length must be 1.5 times the height, what is the maximum volume? Complete the reasoning model below to find the volume. Well, starting off, the volume of the camera, we're going to be representing that as a V. Just because, well, that's how you normally represent volume. The height of the camera, which is going to be basically what we base everything off of, is going to be considered your X value. The length of the camera, if we look up at the top, the length must be 1.5 times the height, which means that we're going to be putting a 1.5 times the height, or times x right here. And last but not least, the width of the camera will end up being 4 minus the x plus 1.5x. The x plus 1.5x is going to be what the height and the length are added to together, which means that the remaining little bit is where we get the width. So that is why we have a 4 minus all of that. So using that information at the very top, I'm going to keep it on the page, we must circle the graph of the function. And as you can see, we already have that one function previously circled. In this case, it's going to be going downward, and we're going to have two different turning points. We're going to have a turning point, it looks like at 0, 0, and another turning point at a certain area. Now, in order for us to have a maximum feature, essentially what we're trying to find is the relative maximum. In other words, we're going to be trying to figure out where that point, right at that turning point, happens to be at. So, let's use Desmos. Once we typed in the original equation, you can see that we have our graph. The graph is going to be at the point 0, 0, as well as right here we have 1.067 and 2.276. The y value, remember, is going to be our volume. That is our v value. So we know that our y value is going to be 2.276, which means that our volume is going to be 2.276. The x value is going to be whatever our x ends up being. So if I were to go back to our PowerPoint, I can now put that the volume for this problem is going to be 2.276, and the height of this box is going to be 1.0667. Knowing that, that is our x value once again, find the length and the width. Well, the length was 1.5 times the x value, or times the height. In this case, that's 1.5 times 1.07, so the length is about 1.61. The width is going to be the orange portion, so again, we're just going to plug in our 1.07 into all the x values, and you'll get a 4 minus the original, and then we have 4 minus 1.07 plus 1.61, which is going to be roughly about 4 minus 2.68, which equals about 1.32. Therefore, the height is going to be 1.07, the length is 1.61, and the width is 1.32. And we finally made it to the lesson check. Write a polynomial function h that has 3 and -5 as zeros of multiplicity 2. The expressions x minus 3 and x plus 5 are going to be the factors of polynomial, because essentially what we have to do is, since our answers, our solutions, are 3 and -5, we must do the opposites to get to that factor portion. So that 3 became the x minus 3, that -5 became a positive 5, or x plus 5. If I were to write this polynomial in factored form, you would get something that would look like this. Notice, multiplicity of 2 means that both of these need to happen twice. In other words, it would be like me writing them twice. So we would have x minus 3 times x minus 3 times the x plus 5 times x plus 5. However, if both of these share the exact same thing, they both look identical, which they do, x minus 3 and x minus 3, we don't have to worry about writing them twice out. We can just put that square, and that square will represent the multiplicity of 2. So the answer, h equals x minus 3 squared times x plus 5 squared, will be the polynomial function h that has 3 and negative 5 as zeros of a multiplicity of 2. I hope everyone has a wonderful day. Stay out of trouble. Don't do anything stupid. And I'll be seeing you guys in the next one.